Elements, they're pretty cake. The smallest particle of an element is an atom. You know, we think of that as a little small circle. So these little small circles of sodiums and these maybe a little bit bigger circles of iron, because we know all atoms can't be built exactly the same. Helium's probably really itty bitty small little particles. Neon's not much bigger. You know, they're gases. But that, you know, we think of them a lot like that. These kind of small spherical objects that are essentially running around all around us. And even if they're not running around like iron wouldn't be, or sodium, they're at least housing things, and they are actually moving at all times. So that's a pretty kind of basic. That is the smallest unit of matter is an atom. Okay, and those atoms are atoms of certain elements. Okay, now those atoms sometimes come together. For instance, you could have an atom of sodium and an atom of oxygen. And if you had two atoms of sodium, what would happen is these two atoms would essentially make a compound, and you would make sodium oxide. Okay, iron does this as well, a little more complex, but iron could make either iron 2 or iron 3 oxide. Essentially, it's your rust that you see on a car. The rust you see on a car is a little more complex than just one of those two compounds, but it is an oxidized form of iron. That has come together to make a brand new compound. And that stuff is pure. Why is it pure? Because it has a fixed composition. Okay? No matter when you find it, if you're talking about, you know, this certain iron rust, then you're always talking about, in this case, Fe2O3. It's always that composition. End of story. When you're talking about sodium oxide, it's Na2O. That means there's 2 atoms of sodium for every 1 atom of oxygen, which is really cool. I mean, it doesn't matter where you go on this planet, you're going to see that. You could go to China right now and go find somebody to sell you some sodium oxide, which is going to be really hard to find that person. But you can find a person, scientific company or something, and they'll sell you some sodium oxide. It'll be sodium oxide, 2 NAs and 1 O in this fixed composition. It's always going to be that way. Water, our good old familiar friend, H2O, is always H2O. We always refer to it like that. Take it for granted, H2O. Well, what does that mean? That means that no matter where you find water, if it is water, that is 2 hydrogen atoms with 1 oxygen atom every time. And that is one of the coolest things. That's actually a law of definite proportion sort of thing. That even goes into the mass of the things and everything like that, which is very interesting. John Dalton got into all that. But the basic idea is the same, that these things have a fixed composition no matter what happens. Now, of all these pure substances, what's the most common? One of the most common elements that's out there is oxygen. Oxygen is by far the most common, somewhere around 45% abundance in the world. It's kind of interesting. You think of oxygen being, you know, this most abundant of all elements. However, it's a gas. Man, oxygen's a gas. Well, you know, jump on the ground and boy, I mean, if most 45% of a lot of the stuff that's around me is going to be oxygen, then how the heck am I not just falling through the floor right now? Well, what happens is that oxygen forms compounds. And you'll find a lot of the oxygen in the world in compounds. 2 main compounds really house it: water and silicon dioxide. Sand. Good old sand forms into glass later on. But essentially, those are your 2 big oxygen-containing compounds. Also, your rusting objects like iron, they're going to be oxidized. Aluminum gets oxidized. Zinc, nickel, they all oxidize. When you find them in the real world, you actually find them as the oxidized form. And that's what's kind of neat. You never really find a lot of those individual elements by themselves out in the real world. You're going to find them as a compound. Sometimes oxidized, a lot of times oxidized. And what you'll have to do is, if you want that element back, you're going to have to purify it. Well, how do you purify it? Well, a lot of ways to do it. Mercuric oxide, HgO. Mercuric oxide, actually a chemist earlier on actually was able to decompose this back to mercury by essentially magnifying sunlight, heating it up hot enough in order to get it to do that. And that's really cool. That's a chemical property of it, that it can actually decompose at a relatively low temperature, which is kind of cool. So the fact that mercury oxide is, you find a lot of mercury like that. Well, how do you purify something like that? You heat it up. A lot of elements you can do that way. Not all. In fact, there is a good substantial portion that you have to do another process called electrolysis. Okay? Water is a common electrolysis ingredient that a lot of people talk about. But you can do this with metals, namely aluminum, which is your most abundant metal. Aluminum is a purified element that you normally don't find aluminum just out in the real world as aluminum. You don't just go get foil and hey, look, Daddy, I found some foil. Roll some foil out of the ground. It doesn't find it that way. What you got to do is you find aluminum oxide, which is Al2O3, and what you do with that is you then electrolyze it, apply a really high voltage to it, and with that high voltage, you're able to separate the metal from the non-metal, which is oxygen. In this case, water undergoes a electrolysis reaction in which you make 2 hydrogens out of it, and you also make an oxygen out of it. And those are diatomic elements. There's 2 atoms that actually make up the individual particle. So water can undergo that electrolysis to do that. And really all you have to do is it's about 6 volts, put it in there, and it'll start rocking. Direct current, not AC. AC wouldn't work for that. But electrolysis is this great process of doing that, and that's how we get a lot of our purification out of it. So the next question would be is, what do you do if those 2 elements, or 2 compounds, or an element and a compound, or compound and element, what if those actually tend to come together but don't actually chemically bind in some way, shape, or form? Okay, not a problem. That happens all the time. In fact, you exist in one. Well, I'm actually intaking one right now. There are called mixtures, and there's 2 kinds of mixtures out there. There's the heterogeneous and the homogeneous kind. Okay? Heterogeneous are the ones that a lot of people visually think about. Think about heterogeneous as something like muddy water. You think of heterogeneous as salad dressings, Italian, ranch, a lot of those. It's not the same throughout. No matter where you look, you have this composition that's oh so slightly different than so many other places in it. Granite, if you have a granite or marble countertop, you got a heterogeneous mixture there. You look on that granite, and the granite has different kind of marble looks on it and things like that. You actually even have little speckles if you have certain kind of granite countertops. And those are actually causing you to get different mixtures. And you have a heterogeneous mixture with that. The other type of mixture you have is a homogeneous mixture. Homogeneous mixtures are your solutions, okay? Whenever you hear us talk about the word solution, know that we're talking about homogeneous mixtures. Those solutions are essentially when something gets dissolved, okay? Salt water, saline solution, that if you've ever been to the hospital and you've actually had to get a saline injection or a saline IV, you've gotten a solution put into you. Gatorade is a solution. It sits there, it's sugar and salts dissolved in water, and when you imbibe it, no matter where you seem to drink it, it always seems to have the same flavor. Tea, as long as there's no ground up leaves left over or anything like that, or coffee with no ground up coffee grinds left over, you got yourself some homogeneous mixtures. You exist in a homogeneous mixture right here. Air is homogeneous. We so much think of homogeneous mixtures and solutions. You hear the word solution, you're thinking, oh, that's something with water. It's not always with water. In fact, gases can be the solvent as well. Solids can be the solvent. If you play lacrosse or hockey, you probably have an alloyed instrument that you're using with. A lacrosse stick actually uses steel and chromium and a few other elements in order to get some more composite alloys. Aluminum alloy is really good too for a lot of stuff. Lightweight, strong if you actually mix it with the right stuff. For metal alloys, you have to heat those up a little bit more. You melt them, you kind of swoosh them all together in the liquid phase, and then you let them solidify. And as they solidify, they have that nice homogeneous solution throughout them. They're called alloys then. Okay, so solid, homogeneous, we call alloys. Pretty much everything else we call solutions. Even our air that we're existing in is a solution, because no matter where you go, it's good old air. About the same percentage nitrogen and oxygen anywhere else as you're going to go.